Okay, in this video I want to show you how to find derivatives of exponents and logs that involve other bases. So, in case you want to know where it comes from, let's say you want to find the derivative of y equal a to the x where the base is not e but it's some other number like 2 or 3. Well, what you could do is you could take the natural log of both sides, and when you take the natural log of the left you just get natural log of y. But remember, there's a log property that says when we take the natural log of a to the x, that's x times the natural log of a. Now remember, natural log of a is just a constant like any other number like 3 or 5, but it's just a constant natural log of a where a is a constant. So if you take the derivative of both sides with respect to x, so let's say you take the derivative of this side with respect to x, and then you take the derivative of this side with respect to x. Well, the derivative of natural log of y is y prime over y, or you could say it's 1 over y times y prime. And the derivative of x times natural log of a, remember, the derivative of any constant times x is just the constant. So the derivative of natural log of a times x is just natural log of a. So now we've got y prime over y equal natural log of a. So what does y prime equal? Well, multiply both sides by y and we get y prime is equal to y times natural log of a. So ultimately, since we knew in the very beginning that y was equal to a to the x, now we can say that y prime is just a to the x times the natural log of a, which is basically this formula here. So the derivative of a to the x is natural log of a times a to the x. So how does that work? Well, if we just wanted the derivative of 3 to the x, the derivative of 3 to the x would simply be 3 to the x times the natural log of 3. And that's pretty much it. Okay, now, what if I wanted the derivative, the derivative of a log that's not the natural log, but it's the log of x by using some other base? Well, jump up here and remember that anytime you write the log of x base a, you can actually write that using the change of base formula. You can write this as a base e log. So I can write this as the natural log of x over the natural log of a. So that's just the change of base formula. So now, if I want to take the derivative of y equal log of x base a, it would be the same as taking the derivative of this function. And again, remember, 1 over natural log of a is just a constant. So the derivative of 1 over natural log of a times natural log of x would just be 1 over natural log of a times 1 over x, because we know the derivative of natural log of x is 1 over x. So how does that work? Well, it's this formula down here, right here. So how does it work? Well, if you want to take the derivative of log of x base 2, then based on that formula, it's going to be 1 over the natural log of 2 times 1 over x, or just write it as 1 over x times the natural log of 2. Now, both of these can be extended using the chain rule to where instead of x, you have u. So if you want to take the derivative of a to the u, where u is a function of x, well, it works the same way. It'd be natural log of a times a to the u, but remember, you have to extend the chain rule, so you get times u prime. So how would that work in this case? Here I have a to the u, where u is 5x squared. So the derivative would be, it would be 3 to the 5x squared times the natural log of 3, and also times the derivative of 5x squared. And remember, 10x is the derivative of 5x squared. Now, the order in which you write these is not really that important, but just be careful with this exponent that you don't get it caught up with one of these other factors. So 10x times 3 to the 5x squared times the natural log of 3 is the answer. Now, if you wanted to do one for the log of u base a instead of the log of x base a, Well, it works the same way as this previous one did here, except this time you still have 1 over natural log of a times 1 over u, but then you have to multiply again times u prime. So if I wanted to find the derivative of log of 1 minus x squared base 5, well, I would have 1 over natural log of a, so that's where the natural log of 5 comes in the denominator, and then I have 1 over u, so that should be 1 minus x squared there, so 1 over 1 minus x squared, and then times the derivative of 1 minus x squared. Just a second, I'll show it to you a little bit better format. So if you look down here, you'll see I have 1 over natural log of 5, that's the a, and then I have 1 over 1 minus x squared, that's the 1 over u, and then I have times minus 2x. Well, that's the u prime, that's the derivative of 1 minus x squared. But when you put all this together, the top is just going to be minus 2x, and on the bottom you have 1 minus x squared times natural log of 5. So that's how you differentiate using other bases. Okay, now here's something I like to share with people. Alright, we know how to take the derivative of a constant raised to a constant, because the derivative of a constant raised to a constant is still a constant. So the derivative of like 5 to the pi would be a constant, and we know the derivative of a constant is 0. We know we can differentiate a function raised to a constant power using the power rule. So if we wanted to find the derivative of this, we could use the general power rule and get 3 times x squared minus 5 squared, and then times the derivative of the inside. We also know that we know how to take the derivative of a constant raised to a function power, because we just saw that rule that if we wanted to take the derivative of 3 raised to the x squared minus 5, that would simply be natural log of 3 times 3 to the x squared minus 5, then times the derivative of x squared minus 5. But what if we had a function raised to a function power? Okay, well, here's how we would attack that. So here I have y equals 1 plus x, so that's not a constant, that's a function, raised to the x, so that's raised to a function. Okay, so you cannot use any of the rules we've talked about so far, but there is a way to attack this. And it's kind of the way I developed the formula for the exponential functions. So what I'm going to do first is I'm going to take the natural log of both sides. Now, remember, using the power rule, that tells me I can bring the x down now and write it as a factor. So now I have natural log of y equals x times natural log of 1 plus x. And then now I can implicitly differentiate both sides. Well, implicitly differentiating natural log of y would just give me 1 over y prime. But if I implicitly differentiate this, this is a product where the first factor is x and the second factor is natural log of 1 plus x. So let's take x times the derivative of natural log of 1 plus x. Well, that would be x times 1 over 1 plus x. And now let's take natural log of 1 plus x times the derivative of x. Well, that would just be natural log of 1 plus x times 1. So we would get this. So now, I've got these two terms. I've got x over 1 plus x plus the natural log of 1 plus x. But that's not equal to y prime. That's equal to y prime over y. So to get y prime, multiply both sides by y. And so I get y prime equals y times that sum, x over 1 plus x plus natural log of 1 plus x. But you might think that's as far as we can go, but if you go back to the very beginning, remember in the very beginning we actually know what y equals. We were given y in the very beginning. It's just 1 plus x to the x. So the derivative, replace y with 1 plus x to the x, and now I get the derivative is 1 plus x to the x times the quantity x over 1 plus x plus the natural log of 1 plus x. Okay, that pretty much completes finding derivatives of exponential and log functions. And now I'm going to go into the next section. I'm going to talk about integrals that involve exponential and log functions.